So our second speaker here is Professor Jian Jin. He's an associate professor from the Department of Agricultural and Biological Engineering. Prior to joining Purdue, he was also the technology leader at DuPont Pioneer, where he worked on a new controlled environment phenotyping system. So this is going to be a somewhat very radically different talk. It's more on agricultural engineering, machine vision, image processing, and so on. The title of Dr. Jin's talk is Robotics and Data Infrastructure for the Coming Realization of Digital Agriculture.
Thank you. Hello, everyone. You hear me okay? Online is okay. So thank you for the introduction. So I'm an engineer, so developing sensors and robotics. Basically, my research work is to try to collect all kinds of the data around the crop plants, forestry plants, to try to understand what is going on in the field or in the forestry. So for example, if people are concerned about nutrient stresses or diseases, and people care about the disease transfer in the forest area at the regional level, can we detect something and store the data in our computer and apply the advanced algorithms and models to try to understand what is going on in those scenarios? So I think this is my short resume. So I got my PhD from Iowa State. And before coming to Purdue, I worked in industry for DuPont Pioneer. Now the company's name is Corteva, one of the biggest seed companies in this country. So I used to be the imaging scientist and the technology leader working on plant phenotyping. And here at Purdue, my work is still to develop the new sensors to digitalize the representation of our plants and both crop plants and tree plants. So today's topic is about DigiTwin, right? So I think my contribution of today is to give you an idea about how we are collecting data in agriculture and how we can build such kind of the digital models in our computers to represent agriculture so we can do something on our computers instead of, for everybody, everybody has to come to the field and touch the soil, and the environment is usually not very comfortable in our field. Although I love my fields, but believe me, in summer, in a very hot summer, it's moisty, it's hot, the sun is burning you, and all the blades of the leaves are cutting your skin. And then sometimes, the bush is so dense. Sometimes in order for me to reach some area, I need to use my both arms to cover my face and push myself into a bush. Could you imagine that? So the ideal future is, can we do something like what Iron Man is doing here on this screen? Can we represent our field in our computer with a virtual reality kind of a thing? Any type of the data infrastructure, so we can represent our data, report our data, analyze our data, and try to share and link the different people's data together for the whole community to collaborate together in agriculture. So this is our dream. This is the beautiful future, right? But let's take a look at the reality. The reality right now, farmers and the plant researchers, we are still walking into the field to do things like this, like what the pictures are showing. The last picture on the lower right corner. So when you see something like that, you see some yellowness. You see some of the suspicious stress on the plants. Right now, with human eyes, looking at this kind of the picture, it's still very difficult to make a decision whether this is nitrogen deficiency, phosphorus, potassium, probably not tar spot, but some kind of other diseases might be going on with the root, for example. So all those are the questions we still cannot answer. So many of you know that McKinsey several years ago released a report saying that agriculture is the least digitalized major industry in the whole world. Well, this may not be a surprise because agriculture sometimes is kind of behind the other, disciplines compared with Elon Musk's, EV vehicles and spaceships. So many people may think that agriculture is behind just because we are lack of technology or people are not interested in agriculture, or we are investing not enough in agriculture. But in my personal opinion, these are not the true reasons. In my opinion, agriculture is now the least digitalized, not because we're not paying attention to agriculture, but because agriculture is actually demanding way much more high technologies and more research than in other areas. So for example, looking at this Iron Man picture, some people may ask in DigiTwin, think about what DigiTwin can provide us in agriculture. So maybe one question, a potential question is like, can we do something like the nuclear, like the atom bomb explosion? Many countries, they can use the computer to simulate the nuclear reactions, that kind of the models. So can we do breeding with this kind of the computer model? And now we are far, far away from that, just because we do not understand, for example, how the genomes are transferred to phenomes and how the environments are having impacts to our plants. Of course, we have a lot of the researchers studying how the environment and the plant growth are interacting with each other, but there is way long distance to go to understand. So give you just one example, we still even do not understand why the hybrid vigor happens. We do not understand that. Then how can we do breeding with a digital model? So in my opinion, what is the real opportunity and the current leading edge kind of the area for digital forestry, for DigiTwin's role in agriculture? I think, in my personal opinion, I think the best chance right now is to do the better and better quality of phenotyping. In other words, can we develop higher and higher signal over noise data collection tools so that we can apply those sensors in our field and measure. And so hopefully we can detect, for example, before the nitrogen stress can be detected visibly by human eyes, we have our sensors to detect that several days earlier, or even just 1 day or 2 days earlier. And that will really help our farmers to make better decisions, do the smarter farming, save the money for fertilizers, increase the yield because they can avoid the loss caused by the stresses and avoid the pollution, because many people are worried about the over-fertilizing pollution. So I came from Iowa, just to let you know, every year, I lived in Des Moines area for about 5.5 years. So the biggest newspaper in Des Moines is Des Moines Register. Every summer, the Des Moines Register, for continuous several days, they report how the Des Moines water plant is spending millions of dollars to deal with the nitrogen pollution in the Raccoon River and the Des Moines River, because those are the water source in Des Moines City. So a lot of the issues, but if we can develop the better sensors, we can help the people to make better decisions. And I think that is how digital agriculture can play a very realistic role to help people to live a better life in agriculture now. So basically, this is my envision. Here is the Envision Center. So this is my envision about what we hope can be happening in the next 3 or 5 years. So if we can have digitalized and advanced sensors to measure the plants, to determine the MPK levels, to detect the tar spot disease, the northern blight disease days earlier than human vision capabilities, we will win this war at least for a few years, and then we move forward. So for the next maybe 20 minutes, I'm going to share with you our work at Purdue. So if you agree with me that if you agree with me with this conclusion that the sensor quality is the key, and also if the sensor quality is the bottleneck right now to push the digital agriculture into some practical uses to help the people economically. So for the next 20 minutes, I'm going to just introduce you what is going on at Purdue for the plant sensor development. What kind of the data are we collecting now? And also what kind of the robots can be combined with the sensors. So what kind of the robots are moving in our field every summer to help us to collect this kind of data and provide the knowledge and intelligence for farmers. So for the first part, I just want to show you, this is like a gallery of our newly deployed high throughput automatic plant phenotyping facilities. 3 of them are indoor. Actually, the first 3 of them are all located in campus. So all the 3 of them just south of the Lily Hall, which is about 5 minutes away from us. And actually, if you have a chance to visit the southern campus, especially when you use the Harrison parking ramp, if you use the elevator, you can actually easily see some of the greenhouses with the conveyors moving, with the imaging stations having the door automatically open and close to have the plants in and out. And besides these indoor greenhouses, we also have the field, like the gantry imaging system I'm showing you in the last image, which can allow us to simulate the drone remote sensing platforms. The gantry is kind of like a mock drone system, allowing us to carry the weatherproof imaging sensors to simulate this kind of the drone remote sensing. So as you can see, in the recent years, it has been really exciting. So we have been deploying one facility after another facility continuously. So that makes Purdue positioned at a leading position in the nation, talking about the phenotyping capacities with all kinds of the different imaging mode. As you can see, in the first facility, we're moving the plants through the conveyor systems to the fully automated hyperspectral imaging tower in the greenhouse. And in the second greenhouse, we're actually keeping the plants still, but move the sensors towards the plants. So in each mode, you have some advantages and disadvantages. And then how can we do that in the field as well? And also in our AAPF facility, we not only can image the canopies above the ground, but also the roots. We have the CT root scanner to scan the very clear and beautiful root 3D structure images underneath the soil. Just a little bit details. I'm sorry for this flipped. So if you don't mind, maybe turn your head 90 degrees. Sometimes the format changes. But anyway, as you can see in this tower, it's fully automated. So each time the door opens, one plant is pushed in, and we have the RFID reader to understand what is the ID of the plant. And through that, we can check a lot of the metadata, including the genotype, planting date, the treatment, who is in charge of this plant. And then inside the tower, we have the two hyperspectral scanners, both top view and side view, taking one scan. And actually, this tower is very advanced with another function, so that before the scanning, we actually take another very quick snapshot, and then we actually use that snapshot image to determine the major axis of the plant, and then rotate this plant for the plant to face the side view image with the best angle. So this is some details, and welcome to visit us if you have time. Contact me. My email can be found on Purdue website. And with this one, this is our indoor simulation facility using the gantry to carry a bunch of the cameras, including 2 hyperspectral cameras, both linear and spectrum, basically to cover all the way from visible range to near infrared to 2,500 nanometers, and also the LiDAR, thermal, and RGB cameras, whatever you imagine people are carrying with a drone flying above the farm field. We are carrying that, and we are just doing that all through the season in the greenhouse, which we cannot do in the field in West Lafayette, as you know. Just one last one about the facilities, about the field gantry. So as you can see, we can move this hyperspectral camera back and forth just to simulate how the drones are flying in the sky to take the images of the crops. And I just want to spend maybe 15 seconds to tell you some interesting discoveries. So for this chart, the data at the bottom of this slide, the x-axis is the time axis. So basically, we imaged from the 31st days after planting, when the plant is about, we call it V9, that is when the plant is about my chest height. And then we kept imaging for 30 days. And every day, as you can see, we started the imaging every day from sunrise and stopped from sunset. And we just continuously repeating this imaging throughout the whole day. So every day we can scan hundreds or 1,000 images over just one day. So if you ask us, why do we repeatedly imaging the same field for so many times? The answer is actually in this chart. So as you can see, taking the NDVI, which is basically about greenness, how green the plant is, which is one of the most important plant phenotyping features. Just taking this one for one example, you can see every time the measurement is not the same. It's actually keeping changing not only through the whole month, but also every day, if you zoom in into one of the days, every day you can see there is a very stable V shape. So that means the greenness of the plants, they are keeping dropping every day in the morning and then bounce back in the afternoon. And the amplitude of this variance can be up to 20% every day, just for the raw data measurement of NDVI. What does that mean? You know, I worked for DuPont Pioneer. When we work with the breeders working on nitrogen usage efficiency and water usage efficiency improvement for our corn seeds, we will be so excited if we can improve our nitrogen usage efficiency by 2%. That's a great, significant improvement of our product. But my question is, how can you find the 2% signal among 20% noise? So we all take statistics classes, you know, in statistics 101, we know this is not going well. So this is just one example that a lot of the noises are happening. So basically phenotyping digital models is about data, right? But in agriculture, the data quality is the key. And now the strongest message I want to deliver today with this talk is that please be aware that our current agriculture data collection is suffering from so many noise factors with a very strong and very significant impacts. So only if we can reduce the noise, we can show the signal and we can help people. So the next one, so after, besides developing all those facilities, as I just showed you at Purdue, we are one of the leading universities having all those fancy facilities. But the one question is, how can we benefit more people? So even after spending that $10 million to build the AAPF physical facility, phenotyping facility, our own professors at Purdue are still waiting in a line, waiting for their turn to use the facilities. But we have 600 million farmers around the world. The question is, how can we deliver our sensor data collection technologies to everybody? So the whole world, everybody can easily use the advanced sensing technologies at any location. One idea is, could we implement both the hardware and the software technologies into a small handheld device? So everything is in your hand. Now you can walk to your growth chamber, greenhouse, field, and measure everything as what we're doing in our fancy greenhouses. So the good news is that 5 years ago, we made it happen. So this is the video, short demonstration. With this handheld device named Leaf Spec, it takes only 3 seconds for you to scan a leaf. And immediately after that, 3 seconds after, you can see the nitrogen, water, and other things on your smartphone screen. And each measurement is georeferenced thanks to our advanced computing group's work, the data infrastructure. So we can show the location of each measurement, we timestamp each measurement, and we can combine a lot of the measurements together to make smarter decisions. And one highlight of this Leaf Spec device is that this is a real hyperspectral camera. That means if you take a look at this corn leaf image, each pixel actually has 500 different colors, all the way from 400 nanometer to 1000 nanometer. And you know, our human eyes stops only at 650 nanometer. That means this device can see a wider range, and it can see hundreds of different colors compared with only 3 colors with a healthy human eye. So as you can imagine, this capability is way beyond human vision capability. So that's why we can see diseases and nutrients and the drought stress, the moisture, lack of the moisture in the leaf much earlier than human eyes. Another highlight about why the Purdue Leaf Spec sensor is leading now in the signal over noise aspect. So look at we have hundreds or thousands of the drone imaging platforms flying. Myself is a drone imager as well, so I fly a lot of the drones doing things like that. But over the last many years, I realized that there are a lot of the noises, again, noises, bothering us. So for example, when we fly the drone above my field here, the sun angle is keeping changing. The sun's both intensity and color are keeping changing. We're enjoying the sunrise and the sunset as a red sphere, but over the noon time, it's totally different color and intensity. And the clouds are moving, applying shadows. And if you take a closer look at the canopy image we're taking with the drone, you realize that it's actually there is a great variance of different types of the signals combined there. So for example, you see the very shining, bright spots. Those are actually the specular reflectance. So we're actually looking at the sun through the leaf as the mirrors, a lot of the small mirrors. So basically we're doing sun phenotyping, not plant phenotyping, if you look at those pixels. And sometimes we're looking at the dark shadows and sometimes the soil background, because in remote sensing, if you can have 2 inches pixel size, we claim that is already high resolution. But my question is, with 2 inches resolution, how can you clearly segment your leaf from the soil background? So a lot of the soil background is mixed into your signal. And the slope of the leaf, if we have any professional leaf imagers, you probably know the slope is a big factor in imaging. So that is why we are really limited by all those noise factors. And if the noises are still there, we just cannot see the signal very clearly. And another thing is the resolution. So sometimes we really want to get close, take a closer look, because we need that resolution. As you can see, when the plants are healthy or suffering from potassium or nitrogen deficiencies, the yellow and the green distribution is actually very different. So this kind of the image, if you can have that resolution, you can take a look at the image, and the image can tell you much more than just the general color of the whole spot of the field, which you can see from the sky. So as you can probably imagine, that is one of the reasons why we developed this kind of the family of the handheld devices. Because with this kind of the proximal touch-based sensor compared with the remote sensing, of course, we are much slower, but the advantage is that now you can get much closer. You can block the ambient light. You can fix the leaf slope. So all of those major noises are gone. And now when the noises are gone, we can do better phenotyping. Just to give you one example, so we talked about 2 minutes. So these are just the scenarios how we are doing phenotypings in the field. And because I'm limited in time, I will quickly skip this. And also this, in the future, if I have a chance, I can explain why with the leaf spec image at this level, we can see nitrogen stresses so clearly when the human eyes cannot see any signal, any difference between the high nitrogen and the low nitrogen. But today I really want to show you some of the pictures, some of the videos. So how our robots are playing in the field. So basically, the handheld device is designed for human to operate, right? But again, at the beginning, I talked about how difficult it is to assess any of the locations in the field. The question is, can we develop robots? Some robot with a machine vision to detect this kind of the leaf and drive a robotic arm to replace human being for this kind of the operation. So I just want to play 2 videos. This is in the greenhouse. So we actually developed this. This is actually carried by our greenhouse imaging gantry. So every time we use machine vision to detect the top matured leaf, again, actually which leaf to measure is actually a very important thing, but that's off the topic today. So every time we move to a new location and detect another leaf, the robotic arm automatically drives the leaf spec to grasp the leaf and scan for hyperspectral. And then we moved forward last year to move this to a drone system to be applied in the field. And that was demonstrated successfully again and again. Thank you. Yes, let's play. So last year, we successfully demonstrated this drone robot, which is the same idea, but now it's a mobile platform. Imagine you got a phone call from a farmer with a 1,000 acres farm saying, hey, I'm suspicious about any dicamba drift herbicide stress from my neighbor, maybe drifted from my neighbor. Could you use your advanced leaf spec sensor, which I know is equipped with a model to detect dicamba. So we just carry this drone over there. We don't need to do anything. We just sit on the beach chair enjoying the juice, but we just only need to program a bunch of the locations. So every time the drone will land at each of the location one by one, use the machine vision to detect the leaf. And then the leaf spec will do everything remaining, including scanning the leaf, processing the hyperspectral image, tell you if there is a dicamba stress or not. And so you can see that on your phone screen. And then the drone flies to the next location. So this product is named, sometimes we call it Dr. Pheno earlier, but now we call it Pheno B. And we are trying to commercialize this product with a Purdue founded company as well. So, so basically this drone can actually decide which is the best location to land for the next one based on the real time thing, thanks to our data infrastructure. But I'm going to skip the details today due to the time limit. So eventually I want to come back to this one. So this is the future of digital agriculture in my personal opinion. So hopefully with our advanced sensors and robots, we can help farmers to attach all those automated sensors to any of the existing facilities so they can make better decisions, save the money, boom the yield, feed more people, solve the hunger problem, and resolve the environmental pollution issues as well. So I will stop here. Thank you.
Yeah, that was really interesting. We do have a slight change in the schedule. We have our break now for 10 minutes to 2:10. Our next speaker will be here at 2:10. So in the meantime, we have time for questions, but you can also have coffee and sure.
Thanks. Yeah. So a few slides back when you were showing the view from the UAV and describing the challenges of signal to noise, where you have soil and you have reflection from the sun and trying to map out that physical space. I'm completely ignorant of the current state of the art in this area. So I was curious, has there been any attempt to also have on board those UAVs like a secondary or preliminary imaging system in addition to the science data you're after is the hyperspectral image, and the challenge is trying to see, okay, well, what exactly am I looking at here? Because there's a lot of other stuff in this picture, right? So I want to build like a three-dimensional coordinate system of my field and understand where that is applying. Has there been any attempt to use something like LiDAR or some other secondary imaging system on board to map out the physical space so I know, okay, this pixel's from a leaf, this pixel's from soil?
Yeah, so actually many of the researchers are working towards that direction as well. So some examples are like the work from our civil engineering professors like Dr. Ayman Habib, Dr. Melba Crawford. So they are all working on more and more advanced drone imaging phenotyping technologies. Basically, how can we improve the resolution and combine the three-dimensional things with color things together. So for example, Dr. Ayman Habib is probably the world's best scientist using LiDAR system to measure the 3D canopy shape and combine that, reference that with hyperspectral spectrums together to make a decision. So actually things are going on right now. I would describe this kind of the image. So there are actually two approaches. One is to live with our existing drone platforms, remote sensing platforms, because talking about between remote sensing and proximal sensing, we're basically talking about the dilemma between quality and the throughput. With a drone, we already have the very high throughput. We can cover hundreds of acres very easily, but we are far away from the plants and we are suffering from the environmental ambient noises. If we go closer, we get rid of those noises and we see things clearly, but we are too slow here. So actually I see two approaches. One is to keep using those drone platforms, but we need to solve each of these noise issues one by one. Higher and higher resolution, better and better signal over noise, and then combining LiDAR and hyperspectral, and we can keep moving forward. So people are working on that area. And on another area, which is maybe one unique thing, the Purdue is taking another unique approach, is to, instead of waiting until we solve all those noises, we can't wait. We want to deliver some products for the farmers. Can we quickly take a shortcut to move to the proximal sensor? So we already resolved the quality issues. So we can already deliver some of the products for the farmers. And then we listen to the farmers. How fast you want to be? And we have our robotic technologies to move it faster and faster. So that is another unique approach I'm seeing that Purdue is taking right now, including my lab. Does that answer your question?
Yeah. So the answer is yes.
Okay. Thank you. That's a great question.
Okay, I think we have time for one more question before we go on to the next talk. Are there any other questions? Well, I'll ask one. So as you're working with farmers, like how much concern is there of like data security and essentially translating it to the field? Like are the farmers receptive to this, or do you think there will be challenges there?
Yeah, I think that's another great question as well. So every time when I talk with customers like farmers, everybody is super sensitive about the confidentiality because nobody wants to let other people know what is going on in your home, right? But at the same time, I think I also see some of the customers who are actually asking questions about how we can collaborate with my neighbors. So I will take the dicamba and the 2,4-D example again. So I don't know how many of you heard about the dicamba and the 2,4-D issue, but if you go to any of the farmers conference, and if you interview a farmer, especially in the Middle East, what is the most concerning issue these years about agriculture generally? For most of the times, you'll hear about dicamba. So basically, dicamba is a new mode of action of the herbicide. It's very efficient to kill the grass, but the problem is the genetic modified crops are not popular now, which means the plants which are protected against dicamba is not that popular. So many of the soybean plants are susceptible to dicamba. That means if I'm a farmer, I purchase those seeds. So my dicamba cannot kill my soybean, but it can kill the grass. But dicamba can be lifted to the air with those mixtures and drifted to my neighbor's farm who may have the susceptible plants. So actually, this is a huge issue now. So in order to solve this issue, it's really not just for the independent farmer, but we need the collaboration between farmers because it's a whole regional thing. Because only when I share my smartphone app and my regional map with my neighbors, we understand what is going on. Maybe my neighbor will give me a pre-warning. And then with this kind of the system established, we may tell people when, for example, when is the best time to spray dicamba? Because with our data infrastructures, I see the potential that we may use weather data, weather forecast to give the suggestion. So if your downstream is having another farm field, probably you want to wait until the next day. So this kind of the regulation and the policy has to be achieved by collaboration between farmers, and many of our farmers' customers understand this. So I see a lot of the opportunities, and also for the concern about the confidentiality. I think one approach is that we can use technologies to relieve people's concern, because we can use the encrypted data format to guarantee customers that your data is confidential. And if you want to collaborate with other data, you know, in the Linux system, you can set up different types of the accounts to allow people to keep data confidential, or share with only your friends, or share your data with the whole community. So I think the technology will be the answer. And that is exactly what we are collaborating on the digital agriculture's data infrastructure to relieve people's concern, but to promote the sharing functions and the collaborations between the different groups.
Thanks so much. And again, let's thank Dr. Jin for his talk.